First of all, I would like to thank the organizers for organizing this very exciting conference. And so today I would like to talk to you about a new reproducing kernel formulation to model extreme events where there are several issues to deal with. There's what we call a kernel instability, and then there's a rank instability, in addition to the fact that whenever you try to stabilize those, the spurious modes, there's an issue of accuracy as well. And so how do we try to achieve all these objectives, meaning getting good accuracy, stable solution, and still be able to do it in an effective way, a computationally efficient way. So that's what I'm trying to talk about today. As a motivation of this work, what you see in the middle, on the left-hand side, is a penetration process. This is the blast explosion, and the blast is induced that can be observed by, for example, this blast simulator, which is a hardware that you can generate very high pressure in a few milliseconds. For example, in this case, you can generate up to 12,000 psi of pressure in a few milliseconds. So one can actually use this kind of device to observe very, very detailed on the crack propagation and up to the total collapse of the structures. These are the type of problems we try to simulate. Of course, a starting point of these problems is a continuum problem. Right? You start with the structure, and then there's an impact, high velocity impact, and so there's an elastic response, inelastic, and then fracture and damage until the structural collapse. So to do this kind of computation, you have to start with a good solution accuracy of a continuum system to start with. But later on, when damage initiates so much, it's into these fragmented solids, the particle-like, not really at the level of particles that a lot of physicists are dealing with these days. But we're talking about fragmented solid that behave like particles. And typically, models for continuum system are like finite element method or even mesh-free methods. These are really computational methods for continuum system. Whereas on the other extreme, for particles, as you know, there are also another class of computational methods like a discrete element method or molecular dynamics simulation. These are the methods that start with particle models. So what you do is you deal with particle-particle interactions either by kinematics or by potential force functions and things like that. Now, we have to deal with a problem that starts with a continuum and has to be accurate enough so that you calculate you capture all the key features that damage the material, and all the way up to this level. Can I come up with a numerical method that can do this wide range of spectrum of deformation? And so we found that a mesh-free method is a good starting point for modeling continuum behavior of the materials, even up to very large deformation. For example, plasticity, metal-forming. It actually works out very well compared to the conventional finite element method. But then when you get into particle-like motion, there are issues to deal with. And the first issue is so-called kernel stability. I will show you why there's such issue. But in the layman language, really what it means is that you have to have enough neighbors for the approximation to be able to construct. And when you try to use, for example, linear basis in 3D, you have to have at least 4 neighbors in each of this the cover of this approximation space. And how do you deal with that kind of situation? And then once you have this kernel stability, then you have to deal with quadrature. Because as I said, I'm dealing with continuum problems. So usually you use Galerkin framework to model this continuum problem, and you have to deal with quadratures. But here, we have no choice but dealing with the nodal integration, because in the end of the process is particle-type motion. Well, nodal integration is well known to have rank instability, and it's also poor accuracy in these nodal integration. How do we deal with this type of situation and be able to get good solution accuracy all the way from the beginning to the end? And then in the end, I'll give you some numerical examples. So to explain what is kernel stability, I'm taking sort of 2 commonly used approximation methods that have been used in a lot of literature. This is just a very short list of approximation functions where you start with a discretization of a domain by some points, and at each point you define sort of so-called open cover that covers some neighborhood points. And within each open cover, one will then construct the approximation function. So the unknown is approximated by the summation of approximation functions multiplied by the coefficient. This approximation function, under this construction, is a multiplication of two functions. The first one is called a kernel function, something like this, associated with each point. It defines the locality of the approximation and the smoothness of approximation. Okay, so you can do something like a step function to give you strong discontinuity if you have to deal with cracks, a weak discontinuity if you have to deal with shear band, and then some other continuous function. You can actually get to Cn continuous function, meaning nth order derivatives still continuous without problem. This is actually the part is really free. And then the second part of the approximation is a linear combination of some basis functions. And typically you use monomials. If I have nth order monomials here, and then I expect to get an nth order completeness in the approximation. Okay, so that's how this approximation is constructed. Of course, one can embed some other different non-polynomial type of basis. For example, some characteristic functions near the crack tip if you have to deal with crack problem. And so if you have some prior knowledge about the physics of a problem, you can bring in those characteristics into this set of basis functions. Then the next step is to make sure that this approximation can exactly reproduce those bases. So if I have no monomials, I will have a set of equations that enforce this approximation to be able to exactly reproduce those monomial functions. Okay. So for example, in three-dimensional case, if I wanted to impose a linear completeness in this approximation, then I will have four equations here: an exact reproduction of a constant field, x and y and z. Okay, so here you have a set of equations that you use to obtain these coefficients. So this is a small linear system that you have to solve in order to ensure that the approximation is exact up to nth order polynomial. And as you know, by Taylor series suspension, if I have exactness up to nth order polynomial, then the truncation error is n plus 1, and then that's your error, and therefore you will get L2 error norm. The rate of L2 to be n plus 1, so on and so forth, right? So that's a small system that you have to solve. And if you solve this small system, linear system, to obtain the coefficients, and you bring it back to this approximation function, then there's no surprise that the final form of this approximation function will have an inversion of a matrix, okay? And this is so-called a moment matrix, which is really the Gram matrix of a set of bases that you choose here with respect to this kernel. And it can be shown that if this kernel function is a positive function, this Gram matrix is positive semi-definite in this discrete form. And that's where the problem starts, okay? So there's a possibility that this moment matrix may have a singular value, meaning the zero eigenvalue, and may not be invertible. And what causes that? Well, if you have this set of functions, when you set up these reproducing conditions, when you don't have enough coverage of the neighborhood points, then this set of reproducing equations can be linearly dependent. And when this becomes linearly dependent, then M becomes singular, and this will blow up. Well, this is not a major problem when you are solving a continuum problem, because you know the deformation. You can use your deformation gradient to map back to the undeformed configuration. So if you know how many neighborhood particles that you have to cover, you can set the condition at the beginning, and then you use deformation gradient to check the neighbors, and everything is fine. But whenever you have this fragmented situation, then the deformation gradient is no longer one-to-one, so you cannot rely on that. And so you have to do everything at the deformed configuration, and to make sure that you always have enough neighbor under this kernel support. First of all, you have to check for every node at every time step, and that's computationally expensive. Further, one can try to compromise that. For example, if I use, just constant basis, so I will have partition of unity, right? So that's a minimum requirement for convergence, and I know that will be fine. But it just converges really slowly, because if it can only reproduce a constant field, that means the truncation error is first order. So it will converge, but it converges really slowly. And that's also something that we don't want. So if you wanted to have sufficient accuracy, but at the same time having this moment matrix to be always non-singular, then you have to do something about it. And so, of course, one can say, well, in this case, for example, penetration process, the fragmentation happens near the middle of the domain. So I might just as well use linear basis for the rest of the domain because I still wanted to capture all the wave and all the elastic, elastoplastic response to be accurately calculated. And in the middle, since the material already been fragmented, I can use constant basis because I really don't care about linear reproduction of the polynomials. Well, when you do that, unfortunately, what you have is under this kind of a construction, moving least squares construction, you will get discontinuity in the constructed approximation functions. So this is like a shark wave that you have discontinuity in the field in the field variable, and it also generates something that you have seen probably in other simulation methods such as a numerical fracture, right? In SPH as an example, that this can actually produce the numerical solution in big way if you have all these discontinuity that propagates in space. And so we don't want this kind of situation. So what we can do that we have proposed here is go back to the weighted residual, the weighted least squares residual. That's the starting point of moving least squares approximation. The first term here is a standard weighted residual for moving least squares. UH is the approximated function. U is the nodal value of the function that you try to approximate. You take the difference between the two, square that, and weight this least squares error by the kernel function. What we did is we then add a second term here, which is we pick a few evaluation points near the nodal point, okay? And so I add the value of U, the neighborhood, these additional evaluation points in another term of this least squares measure of the difference between the original function and approximated function. And then you minimize this weighted residual, then you set this x bar, which is where you approximate the function, to be any position in space, right? So that's the idea of moving least squares. Once you do this minimization and this process, then you get this approximation function looks very much like the original reproducing kernel approximation function, except here the vector that contains the basis functions have additional term here. That is the additional evaluation of those basis functions at these few cross points. And the moment matrix also have additional term here. Alpha is a positive number, a small positive number. And you can show that this M star will be non-singular, meaning that this M star is actually a positive definite function as long as these few additional evaluation points have a positive volume, meaning that as long as they are not on the same plane, you can prove that this M star is positive definite, and therefore you can always take the inversion, in fact, regardless of how big the support size is for those kernel functions. And, okay, so with that, here I show you, so do I sacrifice anything, convergence? Well, I'm solving the Poisson problem, and I'm looking at H1. It's important to look at H1 because if you have a numerical method that has only partition of unity, in fact, it's non-convergent in H1 norm. H1 norm is very similar to energy norm. As you can see, if I have only constant basis, meaning that I have partition of unity, it's actually non-convergent in H1. If you use linear basis, then you get a theoretical value of convergence rate of 1 in H1 norm. If I then use this quasi-linear, then depends on the value of alpha. When alpha is a big number, then it's in between solution of constant basis and linear basis. But as long as I reduce alpha to be a small number, then essentially I get the same rate of convergence and accuracy of the solution of linear with linear basis. But I don't need to have enough coverage for this calculation. Here I test the wave propagation problem. On the left-hand side, I create this set of points where the nodal distance is small enough, so if I use the fixed support size of the kernel function, I have sufficient coverage on the left-hand side. But on the right-hand side, I purposely increase the nodal distance so that on the right-hand side with the fixed support size, suddenly now I don't have enough coverage, right? So if you use linear basis, you don't get a solution at all because the solution blow up. You can try constant basis. Well, as I mentioned earlier, that's a partition of unity, but you get this very poor solution accuracy, which is the green curve. If you then use linear basis on the left-hand side because I have enough coverage, and then I reduce to constant basis because I do not have enough coverage on the right-hand side, well, you get a solution, but very poor solution accuracy. This constant basis is just pollute the numerical solution accuracy. Then I use this quasi-linear, and I'm getting the blue curve, which is very, very close to the exact solution, regardless of not having enough support on those kernel functions. Okay, so now I can use this kind of approach to solve this. Oops, I'm sorry. Okay, so the Taylor bar problem, where this one is a constant basis, the solution of constant basis. You see some unstable modes, okay, and then the numerical fracture. I can use automatic basis, start with linear basis, and when coverage is not enough, I switch to constant basis for the domain where the support is too small. Then again, you still get this numerical fracture, something like this. And this is the quasi-linear solution. And here is a comparison with the experimentally measured height, the steady state height of the solution. As you can see that the quasi-linear give you almost excellent agreement with the experimental data. Okay, so now I resolve the kernel stability. Then, as I said, I have other issues to resolve, because now I have to stick with nodal integration. It's known to have poor accuracy, and it's known to have so-called spurious zero energy mode. It's like an hourglass mode in the one-point integrated finite elements, as you all know. So there are some earlier work been done on this so-called stabilized conforming nodal integration. I will do a nodal integration at the nodal points, but I will take the gradient, I will take the average of the gradient and convert that to a boundary integral. And when you do that, you can show that with this kind of a nodal integration, with this modified gradient field, it's like an assumed strength field, but with a special construction of this averaging, that you can show that this kind of a formulation will meet so-called integration constraint for linear basis. And this integration constraint for linear basis looks like a divergence condition. Of course, divergence condition is true for continuum, but when you have quadrature, this may not be true, right? So you have to make sure that the numerical quadrature actually satisfies this condition. And one approach to satisfy this condition is by this stabilized conforming nodal integration with this special gradient smoothing on the gradient. You can satisfy that, you get quadratic rate of convergence, and you also, because of the smoothing, you don't take the gradient directed at the nodal point, so it kills this spurious zero energy mode. But however, there are some small low energy modes that are still there, and those modes can be triggered. In fact, we have actually done some tests. So this is accuracy-wise, this is fine. It gives you the right convergence. But stability-wise, this is still not very good, and we have to do something about it. Of course, this kind of approach is fine for very large deformation problem like a metal forming and things like that. But again, when I have to move away from pure Lagrangian and go to so-called a semi-Lagrangian, where the kernel moves with a material point but not necessarily cover the same set of material points, then I don't want to reconstruct this kind of Voronoi cell, conforming cell at every time step. So you have to sacrifice somehow. You have to relax this condition. In this case, I will just do an averaging, the smoothing of the gradient at the circular domain and transform that to a boundary integral. But in this case, since all these smoothing domains are not conforming, I lose this integration constraint condition. And so I lose accuracy, and I also I have similar stability problem as what I have in this stabilized conforming nodal integration. Now, how do we deal with this situation? I first refer to the recent work on so-called variational consistency in getting nth order patch test. In the finite element terminology, it's called a passing nth order patch test. As you know, typically, if we have linear finite elements, you wanted to pass linear patch test, and there are some tests that you can do to ensure that. Semi-smash-free methods, in fact, it's not that difficult to come up with a condition where you can pass nth order patch test if I have in the approximation nth order completeness in the approximation. And all you have to do is you set up a PD, you set up a manufacturer problem. You can set up the problem of the source term and boundary condition in such a way that you know the solution is nth order polynomial. You preset the solution of the PDE by selecting proper source terms and boundary conditions. And then you set up the variational, the Galerkin equation, knowing that I can construct approximation functions that give me the exact reproduction of an nth order polynomial, because reproducing kernel can do that. And I substitute all these conditions into the Galerkin equation. Finally, you can get this set of equations that's called the integration constraint for nth order patch test. Okay, meaning that if you have quadrature rule, if you're so good to come up with a quadrature rule, that can satisfy this condition. This is a numerical integration of the bilinear form, and this is a numerical integration of the linear forms. Then the solution will pass the method will pass nth order patch test, meaning that the truncation error in the Galerkin solution is n plus 1 order. So you know your L2 norm will have the convergence rate of n plus 1 and things like that. Okay? If you now reduce this general condition to first order, and you can show that this integration constraint is nothing but what I have mentioned earlier, the divergence condition. So now the question is, if I have to deal with nodal integration, so I don't want to mess around with this very complicated quadrature rule. I just wanted to do nodal integration. What do I do? Can I find a way to still make this condition to be satisfied so I recover quadratic rate of convergence? Well, one way you can do it is to note that this integration constraint involves the quadrature rule that you use and also the test function in the Galerkin equation. So one way you can ensure this condition is to modify the test function. Here I add additional basis functions. They are just orthogonal to each other. So it's a very simple constant basis but orthogonal to each other. And insert this into this integration constraint. And from there you can solve the coefficient for the coefficients C. And once you introduce this into this integration constraint, what you can see on the right-hand side is the residual. It's whatever quadrature rule that you choose to your choice that may not satisfy this integration constraint. So you will have a residual. The residual will be on the right-hand side. And then you will use these additional terms as a correction of this residual. So from here, I can obtain the coefficient C by solving a small linear system again. And from there, I can use this method to correct any quadrature rule, any very simple quadrature rule. That does not give you patch test, meaning quadratic convergence in L2 with linear basis. I can use that to correct those simple quadrature rules. So here, I'm taking a very simple example. You know this problem, you know the solution is linear, perfectly linear. And I'm testing all these different quadrature rules. And as you can see, the ones with the black color are the ones that do not give you exact solution, does not pass first order patch test. And here I have a parameter that's a random parameter. I randomly distribute those points. And as you can see, direct nodal integration as NNI or Gauss quadrature, even up to fifth order, with linear basis, I cannot get a solution for a problem where the solution is linear, of a PDE where the solution is linear. So without that, you won't get optimum convergence. The one with red color are the ones that pass linear patch test. For example, SCNI, we know that because this one satisfies divergence condition, so by itself, it passes linear patch test for any random point distribution. Whereas direct nodal integration, SNNI, and any Gauss quadrature order, with this correction, with the correction that I mentioned, can assure you to pass linear patch test. And as a result, here you see I'm solving this problem. The free dashed lines are the ones, very simple methods, that do not give you quadratic rate of convergence in L2 with linear basis, but with the one with solid lines are the one with correction. So after the correction, even something as simple as direct nodal integration, you can get a quadratic rate of convergence, meaning that now you know that you have the right accuracy in the numerical solution. Okay, so the last thing is to recover this rank instability. Well, we know nodal integration will have spurious singular mode. With smoothing of strand in SCNI or SNNI, it kills those spurious singular mode, but it still have some low energy modes that can be excited once you have very high strand rate problem. So the idea we have introduced here is that if you look at the internal energy of elasticity problem here, so what I will do is I first separate this domain into subdomain integration over each nodal subdomain, and then within each nodal subdomain, I'll do a Taylor series expansion. I'll expand epsilon, which is strand, at the nodal point, and plus the first order expansion. Okay? Now the first order expansion will involve the gradient of this strand tensor, and that appears here. Right? So once you do that, then I will then use this as a stabilization. So this stabilization involves the gradient of the strand tensor. So the question now is, how do I compute this? Because I certainly do not want to take many order of differentiation. As you know, for strand, you have to take first order differentiation. For gradient of a strand, you have to take another differentiation. And it becomes computationally very expensive because I have this moment matrix inversion to deal with. I have to take the derivative of that. So it becomes expensive if you have to take more and more order of differentiation, although they are still continuous, but it's computationally expensive. So the idea is, can I construct the gradient of the strand field directly? Well, in fact, what you can do is you can bring in the concept of a reproducing kernel approximation, where I will design this approximation function for strand by using the similar approach of reproducing kernel, where I have a polynomial basis and I have set of coefficients. And then I just impose this gradient, the gradient of a strand, to be able to exactly reproduce the derivative of a strand when the strand is a polynomial function. Okay, so that's how you do it. I will plug in polynomials for strand tensor, and on the right-hand side, I want it to be exactly the derivative of the strand of the polynomial. And from there, I can obtain the coefficients B. And this is under the term so-called the implicit gradient approach. And with that, you can finally construct the approximation function for strand gradient with the form that looks exactly like a reproducing kernel shift function, except that the first term is not 1, 0, 0, is some other different vectors. So computationally, you can see this costs almost no extra cost compared to the original construction of reproducing kernel. Here I have a comparison. This is standard reproducing kernel approximation, and where the approximation function looks like this. This is now the approximation function for gradient, and it looks like this. And the difference between these two set of functions is that, you see, this is M inverse H, and the kernel function is all the same. It's just this vector is different. So when this vector is 1, 0, 0, 0, that's a standard reproducing kernel approximation. When you have this vector, you change it to 0, negative 1, 0, 0. That gives you the derivative in the x direction. You change to this direction, it gives you a derivative in y direction, and this gives you a derivative in the z direction. So by this construction, the stabilization can be done very, very fast with almost no extra cost compared to the case with a direct nodal integration. So here I show you the comparison with, direct nodal integration, as we know, very poor convergence, SNNI also not very good. And now with this naturally stabilized nodal integration, I'm getting close to optimum rate of convergence. Then if you take this one and with the additional correction of this variational consistency of this naturally stabilized nodal integration, then I'll recover quadratic rate of convergence. Okay, and then you can check those modes. The lowest non-zero energy mode is very stable, and it compares very well with a simple test, fully integrated FEM, and you see these two numbers are very close and it's stable, right? So I resolve the stability issue and still be able to get the quadratic rate of convergence. So now let's look at some example problems. Here I have elastoplasticity problem. This is so-called a necking problem. If you use direct nodal integration, because the solution is unstable, so you see instead of getting a necking, you get all these unstable modes. This is where you consume energy. Stabilized non-conforming nodal integration, the same thing. And this is the one, this naturally stabilized nodal integration with variational consistency, and I'm getting the correct necking. I have a comparison with several sets of experimental data. You can see how bad it is if you use a direct nodal integration or SNNI, especially here, this necking radius in the middle is just totally off. But with this new approach, you see it agrees very well with the experimental data. And again, Taylor impact problem, unstable solution, and again, very stable solution, compare very well with the experimental data. So now I'm modeling some penetration problem. This causes the branches of the cracks, and you can see the solution is very stable. There's no unstable modes, and it forms a nice cloud and compares quite well with the experimental data I'll show you here. This is the exit velocity, you can see, and constant basis, automatic change basis, and then quasi-linear reproducing kernel approximation. It agrees very well. We also compare the crater size, because that's really what it matters here in this computation. Not much about the fragmented materials, but this damage in the solid. This blue line is experimentally measured crater size. You see, linear basis, it actually has a poor comparison. Automatic basis is also not very good, but with this quasi-linear basis, it compares very well. With different wall size, different impact velocity, and as you can see, this is again experimentally measured crater size in blue color. I'm not sure whether you can see that. For different wall thickness, it all agree very well. Here, this is the free bullet penetration through the concrete wall. Here, this is a single bullet penetration. This is a free bullet penetration. We compare the damage, the hull, from computation and experimentation. We even compare the bullet deformation of the bullet, and they certainly agree well. More experimental comparison. This is the simulation with the long projectile. Again, agree reasonably with the experimental data. So in the end, I conclude that we have introduced this quasi-linear approximation. So now I have an unconditionally stable kernel stability. Also introduce a naturally stabilized nodal integration to address the null space, possible null space in this nodal integration, and it recovers this optimum rate of convergence with this variationally consistent integration. And now we'll be able to apply this type of approach to many large deformation problems with high strain rate, penetration, and blast type of problems. Okay? So with that, I conclude my talk. Thank you.